Hello friends, in our previous lecture we attempted to move away from the experimentals or test condition and we looked into how to deal with actual mechanical conditions, like the mechanical condition you would experience in a real life situation or in an application. So we considered rather a representative case of such an actual mechanical condition wherein, as opposed to load being imposed along the coordinate axes. So for instance, we have a definite coordinate system and we have corresponding axes that characterizes it. So instead of having the loading directions along one of the axes of this coordinate system, we considered a case wherein the loading direction is rather inclined. However, instead of talking in terms of the loading direction alone, or instead of talking in terms of discussing exclusively in terms of loading direction, what we did was we rotated the frame of reference in such a way that the region of interest that we usually considered also correspondingly rotates. So ultimately what we ended up having was, we ended up having a system like this, where now the loading direction is along the axis that we have been considering so far, and the loading direction resembles the axis that we have been considering in the test cases or the theoretical cases. But what we observe is the region of our interest is now inclined, and we were able to describe the stress experienced by this region of interest AB, and we found that the stress experienced by the region of interest AB is just a portion of the stress that is experienced along the cross-sectional area. So we are considering a sample with uniform cross-sectional area, and it's the loading direction that we are playing around with, and by manipulating the frame of reference in such a way that our region of interest is now inclined, and we want to describe this the stress experienced by the region of interest in terms of the area that we are familiar with, that is perpendicular to the loading direction, and that area we refer to as C. So when you do that, what we end up having is the stress experienced by our region of interest is something like this: area BC, that is perpendicular to the loading direction, and cos theta, where theta it dictates the angle of inclination. So it describes how much inclined is our region of interest when compared to the plane, or in compared to the area that is perpendicular to the loading direction. Now the reason we are interested in BC, or we are focused on BC, or we want to describe everything in terms of BC, is because it is perpendicular to the loading direction P. And now this expression is nothing but this loading direction, or area BC is perpendicular to the loading direction, then it means our described stress, the stress that we have been considering in the test case or the rather straightforward cases or the experimental conditions. So that's the reason we are able to replace it with this without any subscript associated with it. So the stress experienced by AB is a portion of the stress that is experienced by BC region that is perpendicular to the loading direction, and that is the stress that within this given sample, it is the area BC that experiences the maximum stress, and all the other stresses are the portion of it. So all the other inclined planes or inclined areas, inclined region of interest, they experience a stress that is a portion of it. So that is how we have described. So we have considered an actual case that is expressed in terms of the known test case. So using the known stress, we are now able to describe an actual stress. Now, in addition to this, towards the end of the previous lecture, we were able to consider the stress along a specific direction associated with our region of interest. So in addition to, so all the directions that we have been considering thus far is the loading direction alone. So our focus was largely confined to the loading direction alone. This is indicated in red. So the focus was, the only direction that we largely focused on in the previous lecture was the loading direction alone. However, in the last lecture, we considered another direction. This direction is perpendicular to that of the region of interest. So AB is the region of interest. So this is just a blown up representation of what we have here, and BC is the area that is perpendicular to the loading direction, and P is the loading direction. So P is the load, and it also indicates the loading direction. So P is a vector. So it's the load, and it also has a specific direction, and that is represented by red here. All right. Now we are considering a direction. We need to consider a direction that is perpendicular to AB. So this direction is perpendicular to AB. So this we refer to as the normal of AB. So this direction is perpendicular to AB. We refer to that as normal of AB. Now the reason we focus on the normal of AB is because when you consider a normal of a given plane, we will be able to describe the resistance offered by the plane in a more meaningful manner. So that is the primary reason why we considered the cross-sectional area in the first place. When we talked about the test condition, the test tensile loading condition, the reason why we focused on the cross-sectional area that is perpendicular to the loading direction, why we acquainted ourselves with the cross-sectional area in the perpendicular direction, is because it is possible for us to understand the resistance offered by the material along this particular area that is perpendicular to the loading direction, because we are trying to stretch your sample and there are atomic bonds along here. So these are the atomic bonds that are established along this region of interest or the area that is perpendicular to the loading plane, and when you stretch, these atoms get stretched and they offer resistance, and that is the reason why we consider often the area that is perpendicular to the loading direction. And the same way, we here are considering a direction that is perpendicular to our region of interest. Now, when we ascertain or when we estimate the load or the fraction of the load that is acting along this particular normal to that of our region of interest, then we will be able to quantify what is the resistance offered by the atoms arranged along this region of interest. So atoms arranged along this region of interest will offer a resistance, and this resistance can be quantified by considering a perpendicular direction to that of our region of interest. So that is the reason why. So along this particular plane, the atoms are arranged in this manner. So the atoms are arranged in this manner, and they offer a resistance in a direction that is perpendicular to AB. And that's the reason why we are focused on considering a direction perpendicular to AB, and in that direction we want to know what is the fraction of the load that we are imposing along it is acting. So there is a fraction of the load that we are imposing along it is acting along this normal direction. We want to know how much it is. Now, using some geometrical, considering the geometry of the inclined section with respect to that of the perpendicular section BC and the overall configuration of the plane, we were able to show that this angle theta, this one which we have already quantified, the angle that describes the inclination of our region of interest to that of the perpendicular area, this theta is also what we observe when we consider the inclination of the normal to that of the loading direction. This we proved in the previous lecture. This angle here that quantifies the inclination of the normal to that of the loading direction is also theta, which dictates or which describes the inclination of the region of interest when compared to the area perpendicular to the loading direction. So what we observe is the angle or the normal to our region of interest when compared to the loading direction is inclined by an angle theta. Now what we essentially want to understand is what is the stress along this particular direction here. What is the stress along this particular direction, along the normal direction here. So that we can understand by projecting the stress acting along the loading direction onto the normal direction. So the stress experienced by AB along the normal direction is given by P by A cos theta. So A is the area, the cross-sectional area perpendicular to the loading direction. So this we saw in our previous lecture. So this leads to sigma cos theta. Now this sigma cos theta, this sigma AB is acting along the loading direction. It has a magnitude and it is acting along the loading direction of P. It is acting along the loading direction of P. Now what we intend to do is we want to understand what is the fraction of this stress that is acting along the normal AB. So since we have a vector and we want to project it onto another vector that is inclined by angle theta, the way we can do it is when you consider this as the amount of stress that is acting along the normal direction, it is nothing but sigma AB, the stress acting along the loading direction, and cos theta, the theta that is the angle between the loading direction and our direction of interest along the normal. So therefore, when you substitute this, or when you substitute the expression for the stress on AB along the loading direction, the stress that is acting on AB along the loading direction, this when you substitute here, the stress acting along the normal direction would be expressed as sigma cos square theta. So what we have essentially done is, we have considered an inclined plane. We have considered the stress acting on that inclined plane along the loading direction, and this is the expression for it. So this expression here is the stress acting on AB, our region of interest, and the direction of the stress is along P. So along the loading direction, this is the stress experienced by AB. But since this AB is inclined, it is not that much meaningful to us, because we need to understand in terms of the resistance offered along AB and by the atoms. So along AB, the atoms are inclined in this way. So therefore, we are considering a normal to AB. And when you consider the normal to AB, this normal to the stress acting along the normal to AB can be expressed in this manner. And when you substitute it and express in terms of the stress that is already known to us, the stress that emerges from the stress test conditions, experimental condition, we end up having this expression here. Now, what essentially we have done is, we have considered an inclined plane. So we have considered an inclined plane, and we have seen if this is our preliminary loading direction, if this is our preliminary loading direction, and we have seen there is a stress that is acting in this direction. So this is AB. There is a stress acting in this direction, but this is not of much physical significance to us. So therefore, we have considered a perpendicular, a normal to this region of interest, and we have estimated the stress along the normal. So this stress along the normal, we have estimated it. And now, what can also be done is, in addition to ascertaining the stress along or perpendicular to the region of interest, it is also possible for us to estimate the stress along the region of interest. So there are two sections or two directions that are possible. You have the region of interest. It is possible for us to consider a direction that is perpendicular to the region of interest, and that we have calculated it, and not only we have ascertained the direction that is perpendicular to the region of interest, we have also calculated the stress that along the normal, along the perpendicular direction of our region of interest. So we have considered a region of interest, and we have considered normal to the region of interest, and the stress along this particular direction, normal to the region of interest, we have considered it. Now, in addition to the normal to the region of interest, it is also possible for us to consider what is the stress that is acting along the region of interest. So what is the stress that is acting on the surface? So the region of interest is a surface. We have considered a normal, and there is a stress acting on the normal because of the load P that we have imposed. Because of the load P that we have imposed, there is a resulting stress that is acting normal to our region of interest. In addition to this direction, there is also another direction that we can possibly consider, that is along the region of interest. So what we mean by along the region of interest is on the surface, on the desired, on the region of our interest. So not only perpendicular to the region of interest you have a stress, but also on the region of interest you have a stress. Now, is it possible for us to estimate the stress that is experienced by the region of interest on the surface of it? So we have a region of interest, it's a surface. We have calculated, we have seen that there is a stress that is acting perpendicular to it. Now, is there any stress that is acting along it, that is acting parallel to it? So there is it acting on it. So we have a region of interest, is there any stress on it? Not only perpendicular to it, but on it. Now, we have seen that this angle here is theta, and once this angle is known and the stress that is acting along the loading direction is known, we will be able to calculate the stress that is acting along the normal direction. this angle theta is known, and since this theta is known, the angle separating two vectors is known. Now when we project one vector onto the other vector, we will be able to understand what is the stress along the normal direction, and this is how we arrived at this expression here. Now we want to know what is the stress that is acting along AB. So therefore here the angle of our interest is this one. So we want to know the stress that is acting on the surface, on the region of interest. So therefore the angle that we need to consider is this one. Now when compared to the region of interest AB and this green line here, the total angle is 90 degrees because the green line is normal to that of AB. So if you consider this point, this angle as x, the x plus theta is 90 degrees because the green line is normal to. The reason we have this green line is because the characteristic feature of this green line is that this green line is normal to our region of interest. So it means the x, the angle now we are interested in. The reason why we are interested in x is because it helps us understand what is the stress experienced, stress on AB, not perpendicular to AB. The stress is perpendicular to AB, the stress is on AB. So to identify, to estimate what is the stress, the stress that the region of interest AB experiences on its surface, we need this angle, we need to quantify this angle x. So this x is now nothing but 90 degrees minus theta. So in order to quantify what is the angle experienced by a region of interest on its surface, we need to have this angle that is 90 minus theta. Once we have identified this angle as 90 minus theta, then the overall approach remains the same. We have a vector, that is we have a vector that is stress AB that is acting along the direction P. Now we want to project this vector onto the surface of AB that is inclined by an angle 90 minus theta. We have a vector and we need to project this vector onto a direction that is inclined by an angle of 90 minus theta. So all that we then need to do is the stress experienced. So let us use another notation, a difference notation. Stress experienced along, so parallel to AB, along AB is nothing but this, then cos of 90 minus theta. The same approach, we are considering the cos of the angle that separates, or the cos of the angle between one vector and another vector. So we are projecting the vector that is denoted by the direction P onto the vector that is along the surface of AB. So the angle between them is 90 degrees. So we are considering the cos of 90 degrees. 90 minus, so the angle between them is 90 minus theta. We are considering the cos of 90 minus theta. So ultimately what we would end up having is the cos of 90 minus theta is sin theta. So ultimately we would end up having this expression, that is when you are focusing on the stress that is acting along the surface, on the surface of AB, it is the sin theta portion of the stress that AB experiences along the loading direction. So this stress is what AB experiences along the loading direction, and sin theta of it would give you. So when you are inclined, when you are considering an inclined surface and you consider sin theta of it and augment it to the stress experienced by the inclined surface, what you end up having is you end up quantifying the stress experienced by the surface of the inclined plane. So ultimately you now have two expressions. You have an inclined plane, and on the surface there is a stress acting. So if this is an inclined plane, on the surface there is a stress acting, and normal to it there is a stress acting. Now we were able to quantify it by considering the normal and the loading direction, the angle between the normal and the loading direction, and cos of that theta. Cos theta would give you, it helped us project the loading direction to the normal. Now we used the same approach and we projected the loading direction onto the surface. Now therefore what we are able to do is we are now able to quantify two stresses based on this inclined plane, one along the normal, one along the surface. Now this again can be simplified and expressed in terms of the stress that is already known to us. So when you consider, there is an expression for the stress here, the stress that is acting on AB along the loading direction, and therefore when you substitute it, you end up having an expression like this. So a more consistent way of writing it will be sin theta cos theta. So what ultimately we have is the inclined plane is associated with two types of stresses. So the inclined plane here, it is associated with two types of stresses. One is along the normal direction, and this we refer to as, we estimated it to be the stress acting on the plane perpendicular to the loading direction. So this is the stress that we always consider the test stress, the known stress, and this is the theta. It talks about the inclination of the desired plane. So you have an inclined plane, and there is a stress that is acting along its normal direction, and this we quantified it as this. And in addition to the stress that is acting along the normal direction, you have a stress that is acting on the region of interest, on the surface of the region of interest. This we quantified as sine theta cos theta. So we have split this stress that a given region of interest experiences into two components, one component along the loading direction and other component along the surface of the plane. Now these have unique names associated with it, and the stress along the loading direction is called as the normal stress, and the stress on the surface, or the stress along the normal to the region of interest, we called it as normal stress. The stress on the surface of the region of interest, we refer to it as the shear stress. So let me repeat, what we have essentially done is, we have considered a region of interest and we have considered a loading direction, and along this loading direction the region of interest experiences a stress of sigma AB, and this sigma AB we were able to split it into two. From the sigma AB we were able to identify the stress that is perpendicular to the region of interest, that is along the normal to the region of interest. So this we were able to do. In addition to that, we were also able to estimate the stress acting along the region of interest. So normal to the region of interest and along the region of interest. This we refer to as this. Now the stress that is acting normal to the region of interest, we refer to it as the normal stress. The stress that is acting along the region of interest, we refer to it as the shear stress. And because it is a shear stress, it is denoted in this manner, EB. And the normal stress is denoted in this manner. So we can denote it is, because it is referred to as the shear stress, we can denote it in this manner, and the normal stress, the notation for it can be retained. Now the reason why it is called as normal stress is quite straightforward, because this is the stress that is acting normal to the region or the plane of interest. And the reason why this is referred to as the shear stress is because it is perpendicular to the normal stress, or it is acting on the surface. Like when we introduce what a shear load is, we considered, when we we talked about what a shear load means. We fixed our sample in such a way that we are applying load on the surface. In the same way, here the load is being applied. The AB experiences a stress on the surface. So therefore, we refer to it as the shear stress. So from the fundamental description of what a shear condition is, we see that the shear condition is possible when you impose a mechanical condition on the surface. In the same way, here this component of stress is experienced by the surface of our region of interest, and therefore we refer to it as the shear stress. So what essentially we identify is, when you have an inclined plane, and in that plane you are now describing a stress. So this is an inclined plane, and this is your loading direction, and along this loading direction this stress acts. So along the loading direction this stress acts. Now it is possible for us to split this stress into two components, one that is acting normal to the inclined plane and the other that is acting on the inclined plane. So the normal to the inclined plane, it assumes the expression, or we estimate it by sigma cos square theta, or this is equivalent to sigma AB cos theta, wherein the theta, it talks about the inclination of the normal to that of the loading direction, or the theta is also the inclination of our desired plane with respect to the plane that is perpendicular to the loading direction. In the same way, the shear stress is sin theta cos theta, the sigma that is acting, the stress that is experienced by a plane perpendicular to the loading direction, or it is equivalent to sigma AB sin theta, that is a portion of the stress acting on or along the loading direction on the region of interest that is acting now along the region of interest. So you have a region of interest, a stress is acting on the region of interest but along the loading direction, but a portion of it is acting on the surface, and that portion is quantified in this manner. So if you want to consider the different directions, so this is the loading direction. So this is the loading direction D. So when you consider the entire sample to be this, so this is the entire sample, and you are imposing a loading in this direction, and AB is our region of interest. Now sigma AB acts along this direction, and when you consider the tau AB, it acts on the surface of AB. So the shear component of the stress acts along the region of interest, and finally the normal component of the stress acts along the direction perpendicular to the region of interest. So what essentially we have is, in the case that we have considered, we have two components of stresses or the region of interest that we have considered. So we have considered a region of interest that is inclined by an angle theta, and because of this inclination we have two components of stresses, cos square theta, this we refer to as the normal stress, and the other one sin theta cos theta, this we refer to as the shear component of stress. Now again, all these emerges from the reason because our plane that we have considered is inclined by an angle theta. So all this is the splitting up of the components of stresses. Now we have two different components of stresses, the normal stress and the shear stress. This splitting up of the components, the whole discussion on so these two are referred to as the components of stresses. These are possible because we have a valid theta. Now let us see what would happen if this theta, or if let us see what would be the components of stresses when we are just considering a plane that is perpendicular to the actual loading direction. We are considering a plane that is perpendicular to the actual loading direction, then in that case the theta will be equal to 0. So the inclination is because of this angle here. Now what we are considering is, we are considering a plane that is perpendicular to the loading direction, so that means this theta is 0. So plane perpendicular to the loading direction P, and it means the theta is 0. Now when you consider, when the theta is 0, then let us consider the two components, the normal component that is cos dependent on cos square 0, and since cos 0 is 1, we end up having theta. So rather the normal component is sigma cos square 0, and since cos square is 0, we end up having the sigma. And finally, or rather when you consider the shear component of the stress, when the region of interest is perpendicular to the loading direction, in that case we end up having an expression of this sort, sin 0 cos 0, and since sin 0 is 0, the overall stress along the shear direction will be 0. So what we essentially observe is, when we consider a direction that is perpendicular to the loading direction, in that case the normal stress is the only one that has a definite value associated with it, but the shear stress turns to be 0. So when instead of being inclined, when your region of interest is exactly perpendicular to the loading direction, the stress that this particular region of interest perpendicular to the loading direction experiences is exclusively, it's just the normal stress alone. There is no shear stress associated with it, and this is nothing but the ratio of load into the cross-sectional area that we have been considering all along. So this is a generalized case, irrespective of what is your region of interest within the given system. You will be able to dissociate the stress experienced by the region of interest into two components. Particularly in the setup that we have considered, it will be possible for us to differentiate into two components, that is normal stress and the shear stress. Now depending on the theta, the amount of normal stress and the amount of shear stress would vary. Now when your region of interest is completely perpendicular to the loading direction, the shear stress turns to 0 and the normal stress is the only stress that the region of interest experiences again when your region of interest is perpendicular. When your region of interest is perpendicular, this is your region of interest, it is perpendicular to the loading direction, the only stress it experiences is the normal stress, the shear stress turns out to be 0. But as you incline your region of interest, then you have both non-zero normal stress and also non-zero shear stress that can be estimated by these two expressions here, and both are dependent on the variable theta. So cos square theta gives you normal stress, sin theta cos theta, so this gives you the shear stress. So it is sin theta cos theta, this gives you the. Now what we have essentially identified is when your region of interest is inclined, it comprises of the stress that it experiences comprises of normal and a shear component. Both these will be non-zero values when there is a non-zero theta associated with the region of interest, meaning when the region of interest is inclined, both the normal stress and the shear stress will have a non-zero value. However, when the theta in itself is 0, when it is perpendicular to the loading direction, then in that case the shear component of the stress will be completely 0. Now this understanding we have gained by considering a setup something like this. So this is the setup that we have considered in order to show that when you have an inclined region of interest, the stress this region of interest experiences can be dissociated into two components, that is normal stress and the shear stress. So this is what we have considered. However, this is not an actual three-dimensional case. This is just a pseudo three-dimensional case. This is an approximation of a three-dimensional case. So what I mean by that is, this region of interest, that the term that we have been using, the region of interest, the thing is, this region of interest as far as we have considered is just a line. There is no area associated with it. The reason we need to focus on the area is because when you say that there is a specific direction along which the stress is acting, when you say that there is a specific direction, when you are projecting this stress that is acting in this direction onto a direction here, in this case it is rather straightforward to understand because this here is a straight line. So let me give you an example. If you consider a straight line like this, and when you say that this is the loading direction and I'm projecting this direction onto this direction, which is separated by or which is inclined by an angle theta, then it becomes straightforward because we are projecting this load here onto this direction which is separated by an angle theta. Now let us consider an area like this, and now when we say that this is the loading direction and I am projecting this load onto this surface here, what essentially am I doing is I am considering a specific angle theta, and this specific angle theta is not the same all over the surface here, and this specific angle theta is along a specific direction on the surface. So in this case here, one theta is it is all that is required for me to describe the angle between the loading direction and my region of interest. However, when your region of interest is an actual plane, in that case we have restricted ourselves to a specific direction because this theta here is different from what would be the theta along this direction. Even though this direction also is on the same plane, the angle that this vector makes with this direction here will be different. The same goes for the angle this vector makes along this direction here, the same goes for this direction here. So essentially, in this case, it is rather straightforward for us to have a given theta and then to describe or to state that this is the stress that is acting along AB. However, the condition that we are in is not an exact three-dimensional condition, it is a pseudo three-dimensional condition. So therefore, we need to consider an exact three-dimensional condition in order to describe more precisely what is the shear component of the stress and what is the description of the normal components of the stress. So we have considered a system, and this system, even though it appears to be a three-dimensional system, it is actually a pseudo three-dimensional system. We will not be able to make such distinction in the system. So if we want to make such distinction, then we need to consider an actual surface like this. Now what we are essentially now considering is, instead of a line, we are considering an actual surface. Now this surface is our region of interest. Now what we are trying to now do is, this surface is our region of interest, and now what we are attempting to do is, we are attempting to rather rotate our frame of reference in such a way that this region of interest is now perpendicular, but the actual loading direction is inclined. So we are going back to our initial condition. So we started with a condition wherein the loading direction is inclined to our given sample, but we rotated this loading direction by rotating the frame of reference so that our region of interest is inclined. So that is how we arrived at this description. So that is how we arrived at this setup here. Now we are moving, so we realize that this is rather a pseudo three-dimensional setup. All that we need is just one angle to describe the shear stress. So therefore it is a pseudo three-dimensional setup. But when we extend to a three-dimensional setup, it becomes rather bit more tricky, because when you consider just one angle, you are talking about only one direction in the three-dimensional plane. So therefore we need to expand our consideration, and in order to do that, we have rather rotated this AB in such a way that it is now perpendicular. We have rotated the frame of reference back to its original position so that this AB is now perpendicular and the loading direction is inclined. Now in such a case, we have we will move away, and we have, this is our region of interest AB, and in that this AB is experiencing a stress in the inclined direction. This direction is P, and now the normal of this AB, so this AB is here, the normal of this AB is this direction here, and this AB, the normal of AB, the angle between the normal of AB and the loading direction is this. Now irrespective of a pseudo three-dimensional condition or the actual three-dimensional condition, for a given plane, the normal is going to remain the same. So therefore in the three-dimensional case, the normal that we see here, the stress along the normal direction of AB is going to remain the same. It is sigma cos square theta. So this expression is going to remain the same, because pseudo three-dimensional case or an actual three-dimensional case, the normal to the region of interest, our two-dimensional plane of interest, is the same. We will be able to have only one normal. So even if you consider this point here, the normal will be in this direction. Even if you consider this point here, the normal will be in this direction. If you consider downwards, the normal will be in this direction. So all the normals will be parallel to one another. So therefore, we need not, this expression for the normal stress for a given region of interest is not going to change when you compare, irrespective of the system, be it pseudo three-dimensional or the actual three-dimensional. It's not going to change. However, when you now consider the shear component of the stress, then this 90 minus theta, we will be able to get this 90 minus theta only along a specific direction. So only along a specific direction we will be able to establish this angle as 90 minus theta. So only along a specific direction we will be able to establish that this angle is 90 minus theta. So only along this direction we have the shear stress experienced by, so this is in a three-dimensional setup. Only along this direction the shear stress experienced by the region of interest AB would be sigma sine theta cos theta. So what we have essentially done is, we have essentially considered a setup, and in that setup we have now extended the setup through a three-dimensional condition, and in that three-dimensional condition we are now considering a inclined loading direction And when you consider the inclined loading direction, since the normal doesn't change irrespective of your setup, be it pseudo 3-dimensional or actual 3-dimensional, there is no change associated with it. But now when you consider the shear stress, this 90 minus theta relation is possible only in the one direction, and along that direction only we will be able to express the shear stress in this term, wherein the shear stress is the combination of sine theta and the cos theta. So only in this direction alone we will be able to adapt the results that we considered that we derived for the pseudo 3-dimensional case. Now when we want to describe the stress acting on the surface of this region of interest in any direction that is possible, then we need to introduce the frame of references. We need to have a definite frame of references along this surface here. So this is a direction that gives us the angle of 90 minus theta, and therefore we have arrived at this expression here. Now for our simplistic case, for our consideration, we can replace this expression as sigma AB cos theta and this as the sigma AB sin theta, because sigma AB is nothing but sigma cos theta, which is the stress experienced by AB along the loading direction. So now we want to have an expression, we want to have a relation that helps us describe the shear stress, the stress acting on this plane AB, not only in this direction but in all the direction. So therefore we need to introduce a frame of reference, and this frame of reference along the surface, so it can be like this. So this frame of reference, see, is x-axis and this y-axis. So this we are considering a plane, and therefore two axes are sufficient. So we have this as x-axis and this as y-axis. Now what we need to do is we need to find what is the stress acting along this reference, this frame of reference here. So what is the stress acting along this frame of reference? Now what essentially we have done is we have just considered only the solution that we have is, the answer as we have is only for this direction, that is with respect to 90 minus theta. That is the only solution that we have right now. However, what we need to know is, what we need to have is a generalized solution that can be used to describe the stress acting on the surface of AB along any direction. Now we are confined to only one direction because our understanding comes from a pseudo 3-dimensional consideration. So therefore what we need is, we need to have a generalized expression which can be used to describe stress along any direction. So therefore we introduce this coordinate system. Now this direction here, along which the shear stress acts, makes an angle of, let us assume that it makes an angle of phi with respect to that of the x-axis. So this stress here that we have already described, this stress here, this shear stress here, the shear components of the stress that is already known to us, it makes an angle of phi. So this is an angle that it makes with the frame of reference that we have introduced on the surface of AB. So then the stress acting along x, so maybe we can, to make it more clearer, the stress acting along x on the surface of AB will be nothing but the stress AB, the shear stress AB, then cos of phi. So all that we are doing is projecting the stress onto x, and this is separated by an angle, this is inclined by an angle of phi, so cos of phi is included and the stress is included. And now we have already arrived at this relation in our pseudo 3-dimensional case, so ultimately it will be sigma AB sin theta cos phi. So this is the expression that we have already arrived at. So we have along the x-axis the shear stress that is experienced by the surface of AB along the x-axis will be of this form here. Now this is cos theta sin phi. Now it is also possible for us to estimate the shear stress that is acting along the along the y-axis if we consider the extension of the y-axis in the reverse direction. So if you consider the extension of the y-axis here, then the angle this direction makes with the y-axis is 90 minus phi. So what we are doing is essentially we are extending this y-axis in the reverse direction, and the angle this reverse y-axis, that is the dotted y-axis, makes with the shear component of this tau AB is 90 minus phi. Now when you want to then categorize, or then you want to so essentially when you just express these reference systems that we have here, so we have your y-axis, and this y-axis is extended here, and you have your x-axis, and in this direction is the shear component of stress that is acting. Now all that we have done is, this is the surface of AB and I have redrawn it here. So this is the shear component of the stress that is acting on the surface of AB along a specific direction, and now this direction is inclined by an angle phi, and the shear component of the stress acting along x, we have arrived at an expression for it. So these two, it indicate the shear component of the stress that is acting along the x-axis on the surface of the plane AB. Now this angle is 90 minus phi. We have considered the y-axis. Now we want to understand what is the shear component of the stress that is acting on the surface of AB but along the y-axis, and that would be tau AB sine of, rather it should be, since we are projecting this stress onto the y-axis, so it should be cos of 90 minus phi, and ultimately what we would end up having is tau AB sine of phi. Then if you substitute the expression, or if you express this the tangential stress in terms of the normal stress AB, or the stress experienced by AB along the loading direction, it would be sine theta sine phi. So this is the stress or the shear stress that is acting along the frame of reference Y on the surface of AB. So what essentially we have done is, again to sum it all up, what essentially we have done is, we have considered a pseudo two-dimensional case. The pseudo two-dimensional case, it helps us understand that for the pseudo two-dimensional case, the stress experienced by an inclined plane is much different from, it is a portion of the stress that is experienced by a plane that is perpendicular to the loading direction. So we were able to differentiate the sigma from the sigma AB. The stress experienced by a plane perpendicular to the loading direction will be different from the stress experienced by a plane that is inclined to the loading direction. This we arrived from the pseudo three-dimensional estimations. Now in addition to that, we saw that even in the pseudo three-dimensional framework, so it is pseudo three-dimensional framework, even within the pseudo three-dimensional framework, we were able to see the stress experienced by an inclined plane. It comprises of two components. One is a normal component and other is a shear component. So the normal component, it acts in the normal direction. In the shear component, it acts along the plane of the region of interest. Now when we look closely on the on the setup that we are considered, then we realize that the shear stress, the description of the shear stress is rather restricted, because AB is not a line, it is a plane. So therefore this stress that we have that we have described for the pseudo three-dimensional case, it only describes the stress along a specific direction in a plane, along a specific direction in a plane. So this stress, it describes the stress along a specific direction in a given plane. So therefore we extended our consideration to actual 3D, from pseudo 3D to actual 3D. Then we realized that we need to introduce another coordinate system to describe the area of our interest. It is no longer a line of your interest, it is no longer a region of interest, it is a area of our interest. So therefore we need two axes to describe our system. We considered x and y axis, and to ensure that it is possible for us to capture all the directions, we introduced a new angle phi. So far in the pseudo three-dimensional setup, the stresses were dependent on only one variable, that is theta. And even in the three-dimensional setup, the normal stress, the normal component of the stress is again dependent on theta alone, because for a given plane, the normal is always one direction. All the normals are the same. All the normals are parallel to one another. However, in case of shear, we found that we need an additional angle to capture all the directions that are present on the surface of the plane. So therefore, we included a new angle phi, and now this shear component of the stress is dependent on both theta and phi. And ultimately, we have arrived at an expression that shows that within the plane, there are two possible ways of describing the shear stress, and you have two components of shear stress. Even for a three-dimensional case, in addition to one normal stress, the shear stress can be differentiated into two components, and these have two distinct ways of quantifying. We need to quantify, or these have two distinct descriptions associated with it, and they vary with the theta and phi angle. So one is AB, or rather this could be expressed as one description would be one component of the shear stress would be sigma AB sine theta sine phi, and the other description would be sigma AB sine theta cos phi. Now, by varying the phi angle, we will be able to describe any direction within the given plane. So the theta is fixed, and by varying the phi angle, the angle phi, we will be able to describe the stress along any given direction. So therefore, when we are considering a three-dimensional setup, in pseudo three-dimensional setup, what we have is we just have one normal component of stress and the other shear component of stress. However, when you extend your understanding to a three-dimensional case, you have the one normal component remains the same, undisturbed, but now we have two variants or two shear stress condition. So ultimately, in a real life situation, when your region of interest is inclined, you will have one normal stress and two shear stress. So ultimately, what it means is that when you impose a loading condition, an inclined loading condition, or when your region of interest is rather inclined, the stress this region of interest experiences in an actual three-dimensional case, in a physical world, the stress this region of interest experiences can be differentiated into three components. One is the normal component, the other is the two shear components, and these two shear components help us describe the shear stresses the surface experiences in definite direction. So ultimately, in a three-dimensional case, when you consider the components of stresses experienced by a given inclined plane, it has three components of stresses. So it has three components associated with it. You have a uniaxial loading, and this uniaxial loading is inclined, and you have region for a given region of interest. In that case, what we will be able to identify is one normal component of stress and two shear components of stress. So ultimately, the stress experienced by an inclined plane can be dissociated into three components for in a real life condition or in a given three-dimensional system. So with this, we will wind this lecture up. So what essentially we have seen is, we have seen the components of stresses and how it varies with the system that we consider. In the pseudo three-dimensional case, it's just two components. In actual three-dimension, we have these given stress for an inclined plane being different into, or it can be distinguished into three components, one normal component and two shear components. Goodbye.